Hi, my name is Steve Chalk, and I'd like to talk about Cantor's power set theorem proof. I made an earlier video on the proof, and I found that there are many people who don't understand the proof or mischaracterize the proof. So I'd like to clarify some things. I'm going to go through the proof in some detail, but I'm going to assume that the viewer is familiar with set theory and with Cantor's proof. Here's a statement of the power set theorem. For any infinite set X, the cardinality of the power set of X, which is the set of all subsets of X, is strictly larger than the cardinality of X. X is an infinite set. The cardinality of the power set of X is strictly larger than the cardinality of X. If they're infinite sets, this would imply that one infinite set is larger than another. Okay, so how do we compare the cardinality of infinite sets? They don't have a numerical cardinality because they're infinite. So how do we compare them? We compare relative size using bijection as a measure. Bijection is a one-to-one mapping between the two sets. If you can map the two sets one-to-one, then they must have the same size, even if they're both infinite. Note that a bijection is a special case of a surjection. All bijections are surjections, but not vice versa. Hence, we prove that there's no surjection. We also prove there can be no bijection. Okay, here's Cantor's proof. Can there be a bijection between infinite set X and P of X, its power set? If we can prove there's no surjection, we can prove that there's no bijection. And if there's no bijection, then the two cardinalities are not equal. So let's assume that psi, that's that Greek letter there, is a surjection from X onto the power set of X. Let's now define a subset of X, which would be a member of the power set of X, because it is a subset of X, Y, such that for all X that are elements of X, X is not an element of the subset that it maps to, the psi of X. Ostensibly, and this is my point of contention, the set Y must exist under the Axiom Schema of Specification, which we'll talk about. If we can show that it does not exist when psi is a surjection, we show a contradiction and prove that psi could not be a surjection. If psi can't be a surjection, then there can be no bijection and the cardinalities are not equal. So does this set Y exist? The set definition says X is an element of Y if X is not in the subset to which it is mapped by psi. Now, we have an assumed surjection, so every member of P of X is mapped to at least one element of X. Y is a subset of X and a member of the power set of X. Hence, some element of X, we're going to call it X0, which is with no loss of generality, that maps to the set Y. So X0 maps to Y. Now, there's only two possibilities with regard to X0. Either it's an element of Y or it's not an element of Y. So is X0, the element that maps to Y, an element of Y? If X0 is not an element of Y, then X0 fits the defining condition of elements of Y. And therefore, if X0 is not an element of Y, it must be an element of Y. What if X0 is an element of Y? Well, then X0 does not fit the defining conditions of Y. So we can state that if X0 is an element of Y, then X0 is not an element of Y. And our paradox is complete. Ostensibly, this set Y must exist under the Axiom Schema of Specification, but it does not exist if when psi is a surjection. This is a contradiction. Hence, psi is not a surjection. Hence, there can be no bijection. The cardinality of X and P of X are not equal, and the conclusion is that some infinite sets are larger than others. Here's an important side note. Paradoxical sets do not exist. By the axiom of extensionality, sets are fully defined by their members. If the definition of any set implies a statement of the form X is an element of S, if and only if X is not an element of S, then the definition does not resolve to a set and the set S does not exist. Cantor's own proof relies on this assertion with regard to the key set Y. Now, for example, if X is not the null set, then this set definition here, where S equals X such that X is not an element of S, this does not resolve to a set because the paradoxical condition X is an element of S if and only if X is not an element of S obtains. The membership is therefore indeterminate. If you can't determine the members of a set, the set is not defined because they are their members. They are fully defined by their membership. And this would be true even if the paradoxical condition applied to only a single element of X, because the membership would still be indeterminate. In this particular case, S can't be the empty set because every member of X would then meet the condition of S and would be a member of S. Yet if any members of X are in S, then that member would fail to meet the conditions of S and could not be a member of S. So by that definition, S can't be the empty set and S can't have any members. So S is not a possible set and the set does not exist. S is paradoxical and its self-referential definition does not resolve to a set. Alright, let's talk about the logic of Cantor's proof. The method is proof by contradiction, where a proposition is proven to be true or false by assuming the opposite and showing that the assumption leads to a contradiction. The general form here is as follows. To prove A is true, we begin with proposition A. Proposition A should be true. You assume A is false. You then show that this assumption leads to a contradiction. Therefore, the assumption A is false is therefore false, which means A must be true. Hence, the proposition A is proven to be true. And Cantor, his proof follows this general form. Let's look at Cantor specifically. He wants to prove that for an infinite set, the power set of X, the cardinality is strictly greater than the cardinality of the set. Let's outline the specific of each step in the proof, and then we're going to discuss one specific step in detail. The basic proof outline. Proposition A is that there is no surjection from X to P of X. If this is true, the sets do not have the same cardinality. So A, in our general logic, equals no surjection. 2, we assume that proposition A is false, so we assume that there is a surjection from X to P of X, and that would be this psi X onto P of X. Third, we now showed this assumption leads to a contradiction. Cantor asserts the existence of the set Y, a subset of X and a member of P of X. He then shows the subset which ostensibly must exist does not exist under surjection because it becomes paradoxical. So the contradiction is that this set Y must exist, yet if there's a surjection, Y does not exist. The assumption that there is a surjection must be false, and therefore there can be no surjection. Hence the proposition A, there is no surjection from X to P of X, is true. Let's examine step 3 in detail in the larger context of the proof. Under the assumed surjection, the subset defined here must exist by virtue of the axiom schema of specification. That's the claim. The set definition results in a paradoxical condition regarding the members of the set, which takes the form x0 is an element of y if and only if x0 is not an element of y. That's clearly paradoxical. Hence, step 3 concludes that psi is a surjection leads to a paradoxical set definition, and the set, which must exist ostensibly, does not exist if there is a surjection. So the contradiction is this: Y must exist, yet if there is a surjection, Y does not exist. This might be a subtle point, it seems to be for some people. The paradox itself is not the contradiction. A paradox is a form of contradiction, you might say, but it is not the contradiction required under the proof by contradiction form. The contradiction required is that Y must exist, yet if there's a surjection, Y does not exist. And the paradoxical result is evidence of that contradiction. The paradox itself is not the proof's contradiction. The failure of Y to exist contradicts the assumption that Y must exist. Now, why is the paradox not the contradiction, and why is this so important? The distinction between the paradox and the contradiction is important because people seem to fail to understand the proof itself. The proposition is that there's no surjection from X to power set of X, and therefore the proof's assumption that must be contradicted is that there is a surjection. So the paradoxical result of set Y alone does not contradict the assumption. It's the combination of the assertion that Y must exist and proof that it does not exist that constitutes the contradiction. This is important because if we can't assert that Y must exist, if we can show that the set Y may not exist under a surjection, then the proof fails to show the necessary contradiction, even though we could continue to show that Y does not exist. The failure of y to resolve to a set, then, if that's consistent with the assumption of a surjection, then it is not a contradiction of the assumption. It does not contradict the assumption, and therefore the proof by contradiction fails. So if the following two assertions are consistent, meaning they both can be true under the stated conditions, then there is no contradiction. The two conditions, psi is a surjection and the set y is paradoxical and does not exist. Cantor's logic really is equivalent to this. Assume x is not the null set. Define y thus. Y equals a set of x, all elements of x, such that x is not an element of y. If x is not the null set, y becomes paradoxical and y does not exist. Hence, we have a contradiction and x must be the null set. But of course, this is faulty reasoning because we cannot assert that y must exist. Y may well be paradoxical and not exist, and x the non-empty set, in which case these two are consistent, not contradictory. So the question becomes, in Cantor's proof, why must y exist? Do we know that y must exist under surjection? On what basis is it asserted that y must exist? If we cannot establish that y must exist, then the proof by contradiction doesn't have a contradiction. And the justification for the existence of y is generally given as the Axiom Schema of Specification. Now, we could talk about this schema. It's not really an axiom, it's an axiom schema, which means that it's set theory meta-language for constructing axioms, for constructing statements that define subsets. The claim is that any conforming statements are axioms and necessarily resolve to subsets. Any statement constructed in compliance with this schema and not exceeding its limitations is an axiom and guaranteed to define a subset. But of course, there are limitations and they're very important. Here's a formal statement of the axiom schema in relatively plain language. It says, to every set A and every condition S of X, there corresponds a set B, which is a subset of A, whose elements are those elements X of A from which S of X holds. The limitations are that S of X must be a well-formed function, and two, that S of X cannot include a free occurrence of the subset being defined. That would be B in this case. The second limitation is what I want to key on here. S of X cannot include a free occurrence of the subset being defined. In the language of the schema, that would be the subset B. This is intended to exclude set definitions that can result in paradoxical condition. Here's a classic paradoxical set. X is an element of B if and only if X is not an element of B. That is an absurd claim, and it does not constitute a set. Hence, the axiom schema should not apply to this set definition, and it doesn't clearly because we can see that B is a free occurrence in the function, X not an element of B. Now, self-reference doesn't necessarily mean that there's a paradox. You can have self-referential set definitions that are not paradoxical and actually define existing subsets. But self-reference is a condition that renders the axiom inapplicable because it can result in paradox. So when the axiom does not apply, the subset may exist, but the axiom does not guarantee that it does exist. Moreover, if the definition includes or if it logically reduces to the following condition, X is an element of B if and only if X is not an element of B for some X, then we can make the stronger claim that the subset is paradoxical and not simply that it may not exist, but that it does not exist. Let's talk about the axiom schema of specification and how it relates to Cantor's set definition. There's the set definition there. Y equals X, all elements of X, such that X is not an element of psi of X. So that would be the member of the power set to which X maps. Now, does the axiom schema of specification apply to this definition? Can we use that schema to assert the necessary existence of the set Y, or is the existence of Y in doubt? If the schema does not apply, then the failure of Y to exist under the surjection would be consistent with the assumption. If it is consistent, then there's no contradiction and the proof fails. Now, y does not appear explicitly in the definition, as you can see. For the axiom schema to be inapplicable, the condition x is not an element of psi of x must include a free reference to y, but y is nowhere to be seen. So there's a wide consensus in set theory that the axiom schema is applicable, that the set definition conforms to the axiom schema, and the set y must exist. But that assertion depends on an interpretation of the limitation against self-reference as simply being that of free occurrence in the syntax itself. That because we don't actually see y in the formula, there's no free occurrence and the axiom schema applies. Yet, the definition of y includes an implicit self-reference, which would be a free occurrence of y, and it's hidden in the definition of psi. Recall psi is a mapping from x onto the power set of x. If y exists, then it's a subset of x, and hence y would be an element of the power set of x. So y is in the range of, or the image of psi. If psi is a surjection, which is the assumption of the proof, x is not an element of psi of x includes a reference to y. For some element of x, we'll call it x0, psi of x0 equals y, and this is all in Cantor's proof, in fact. So for x0, x is not an element of psi of x translates to x0 is not an element of psi of x0, which further reduces to x0 is not an element of y. The implicit self-reference can actually be made explicit. Recall Cantor's paradoxical set. Here's a slightly more formal definition. There exists a subset y which for all x is in y if and only if x is an element of x and x is not an element of the subset to which it is mapped by psi. So even in plain English, it's a bit of a confusing mouthful. Let's expand this portion of the definition. X is not an element of psi of x. The range of psi is the power set of x, which is an infinite set comprising all the subsets of x. So we could write P of x, power set of x, as a list of the subsets S1, S2, Sn. These are general subsets of x. Now, if y exists, it's also a subset of x, and it would be a member of P of x. So this infinite expansion would be S1, S2, S3, etc., y, etc. Now let's rewrite Cantor's paradoxical set using this infinite expansion of P of x in this function. We can write it this way. There exists subset y for all x, where x will be an element of y if and only if x is an element of x and psi of x equals S1 and x is not an element of S1, or psi of x equals S2 and x is not an element of S2, or psi of x equals S3 and x is not an element of S3, etc. In other words, for each value of x and x, we find the subset to which it is mapped, and then test to see if x is in that subset. Any x that meets these two conditions would be in y. Now, if y exists, it's a member of P of x, so the above set definition is further clarified, and it now includes or psi of x equals y and x is not an element of y. In plain English, for every value of x, we do the following test. X is a member of y if it maps to S1 and x is not an S1, or x maps to S2 and is not an S2, or x maps to S3 and is not an S3, etc., and x maps to y and is not in y, etc. And here we see y as a free variable in its own set definition. Now, in the context of the definition of y equals x, not an element of psi of x, when the condition is evaluated for x0, we get x0 is an element of y if and only if x0 is not an element of y. This is classically paradoxical, and y therefore cannot exist. Cantor himself asserts this in his proof. This is his demonstration of a contradiction. He shows this very paradox. So if psi is a surjection, the self-referential nature of the definition of y is not in doubt. Now, what might be in doubt, or what people claim is in doubt, is the applicability of the Axiom Schema of Specification. What say the defenders of Cantor on this count? Well, some people are not convinced that this self-reference, because it is not explicit in the syntax, constitutes a free occurrence of y. they claim it does not render the axiom schema inapplicable. If so, how do they explain the paradoxical statement that Cantor himself cites in his own proof? X0 is an element of y if and only if X0 is not an element of y. This is a de facto assertion that y is self-referential under surjection, that y is in the range of psi. If it were not, no such assertion, no paradoxical assertion of y would be proffered. Cantor's defenders claim that the surjection does not exist, and they do so by saying that there's no x0 such that psi of x0 equals y. If there's no x0, then y is not in the image of psi, and the axiom schema of specification applies. But this, of course, is circular reasoning. Cantor needs a contradiction, and the axiom schema of specification must supply it. The assumption of a surjection must be shown to result in a contradiction. That assumption is maintained until or unless a contradiction is demonstrated. The axiom schema of specification is not applicable. If it's not applicable to the definition of y, then the logic of the proof does not dictate that we bring the definition into compliance by rejecting the assumed surjection. This is imposing the desired conclusion on the logic rather than the logic compelling the conclusion, and that's circular. The assumption of a surjection is maintained, therefore, and the failure of the subset to exist is accepted. Why? Well, because it's consistent. It's consistent with the assumption. Under the axiom schema of specification, unless it applies under surjection, there is no contradiction. So Cantor's proof basically lives or dies on the applicability of the axiom schema of specification to the definition of y. The definition of y is clearly and inarguably self-referential. The hurdle to get over to convince set theorists that the axiom schema is not applicable is the question of free occurrence, the technical question. Y does appear as a free occurrence in the definition of y when the definition is expanded such that y is not hidden behind the nomenclature. And here it is again. So we can state the following. 1. The axiom schema of specification is not applicable to the definition of y. 2. The assertion that y must exist is not supported. 3. The proof by contradiction is missing its essential contradiction. And 4. Therefore, the proof fails. Now let me respond to a couple objections I've gotten when I've discussed this with people online. Objection 1. Self-reference can be meaninglessly inserted into any set definition. The appearance of y in the expanded definition is therefore not conclusive in the question of self-reference in the original form. My response is that the inclusion of y in the expanded set definition is essential to the definition. It is true that a set definition could be altered to include a circular reference that is totally meaningless, tautological, such as you could say x is an element of y or x is not an element of y. And the set definition would be logically identical to the original and would result in the same set, even though it technically is self-referential. However, it would be absurd to suggest that the ability to include tautological self-reference renders all self-reference meaningless. The test against y in the expanded definition is essential to determine the membership of y, because y is in the range of psi. For this reason, the expanded definition of y is not just logically equivalent, but it demonstrates the self-referential nature of the definition in its original form. Objection 2. The set definition is infinitely long and is therefore not well formed. My response is twofold. First, infinite set definitions are commonplace and there's no prescription on infinite expressions. A common example would be the set of natural numbers, which is often expressed simply as this: 1, 2, 3, etc. The purpose of the infinite expression is to demonstrate the inherent self-reference. Even if infinite expressions are not considered to be well formed for the purpose of the axiom schema, the expanded definition is instructive and demonstrates the self-referential nature of the definition itself. The expanded definition tells us that the axiom schema does not apply to the original definition, because that application would clearly render the axiom schema incapable of distinguishing between set definitions that resolve to actual sets and those that may not or do not. Now, here's some notes regarding axioms. Axioms are not proven. They're statements that are either definitional or consequential and are accepted as definitions or as self-evident yet unprovable true statements. Definitions are not subject to proof or challenge per se, They can be challenged on their consistency, their relevance, their wisdom, etc., but as definitions they simply are. Consequential axioms stipulate consequences that ostensibly flow from definitions. They cannot be proved, but are considered to be self-evident truths and become a basis for proving theorems, etc. An axiom schema, this is an axiom once removed. It's a formula for creating axioms. Axioms are not proven, hence an axiom schema might be said to be doubly unproven. I want to note here that I'm not rejecting the axiom schema of specification. I believe it's a sound axiom schema if it's properly limited, and I'm attempting to properly limit its application. The prescription against self-reference must be robust enough to preclude paradoxical set definitions because they do not resolve the sets. And since much can be hidden in definitions and nomenclature, a syntax-only rule is insufficient to exclude all set definitions that may result in a paradoxical set. Specifically, x is not an element of psi of x hides the condition x is not an element of y in the definition of y. And clearly the condition x is an element of y if and only if x is not an element of y, even if it applies to only one element of x, does not define or identify an existing subset of x. Since that condition can be hidden behind the syntax, syntax is an insufficient testing ground. Implicit self-reference must also render the axiom schema of specification inapplicable. Alright, time to sum up. The paradoxical condition of y is not the proof's required contradiction. The contradiction is the failure of y to exist when the axiom schema of specification ostensibly requires that it must exist. The self-referential nature of the definition renders the axiom schema of specification inapplicable. This can be demonstrated and rendered syntactically with the expansion of the set definition. Y is not guaranteed to exist. Since it may not exist, the fact that it does not exist under surjection is consistent with the assumed surjection. Because it's consistent, the proof by contradiction has no contradiction. Therefore, the proof fails. Thanks everyone for watching, those of you who stayed to the end. I hope it's been educational. I'm perfectly willing to entertain objections and to debate anyone who wants to leave comments in the comments section. The comments are notoriously unreliable, but give it a shot anyway. So thanks very much.
Coming in from London from over the pole, flying in a big airliner, chicken flying everywhere around the plane. Could we ever feel much finer? Coming into Los Angeles, bringing in a couple of keys. Don't touch my bags if you please, Mr. Customs Man.